Hello, class. Okay, so continuing on this subject of gases, we're going to talk about the speed of the molecules in a gas. And it was interesting. I'm going to draw this graph. If we look at the velocity, I'm not going to put numbers here, but because they'll be different for different gases, but they all have this same basic pattern. Then if we look at the velocity of the gas, and on the vertical scale, we look at the percentage moving at that particular velocity. Kind of a tricky thing because of velocity, you'd have to have kind of like a slight width to this. So you can look at like a certain little thickness and say like, what percentage are going to be moving in that range? You can't say like what percentage are moving exactly at that speed because that's always going to be zero. But yeah, so what it's going to look like it's going to look something like this. Now, it's going to depend on what molecule exactly and also the temperature. Higher temperature, they're moving faster. Now, it's interesting that this curve actually came about theoretically long before it could be measured. So a guy named Maxwell that actually calculated this based on like statistical physics, and very, very complicated thing to do. Maxwell was one of the greatest scientists of all time, like really up there with like Newton and Einstein. Definitely one of the greatest of all time. So again, like a velocity of 0, yeah, but then for like this particular molecule, say we have like a peak here, like the highest percentage of molecules are moving around this velocity. Now this raises a question, what is the average velocity of a molecule in a gas? And that's actually kind of a tricky concept because the average velocity of all the molecules in a gas is going to be 0, typically, unless there's like wind or something. And the reason why, picture the room you're in, filled with molecules moving around, and basically half of them, like if you look at all the molecules going to the right, this way, then you have like an equal number moving to the left. And so, because velocity is a vector, the average value, because you have equal numbers going in any direction, they have no preference for going one direction over another, the average velocity is 0, which is not very useful. So we want to come up with a way to define an average velocity for like all the molecules in a gas. And so there's a procedure. The problem with having a velocity, if you like pick a direction, then it could be positive or negative. And so the first step to take an average is to make sure all that the velocities are positive. So what you do is square the velocities. Now you might ask, why don't you take the absolute value? Well, absolute value is, it's one of those piecewise functions where it's equal to one thing, like it's equal to x if x is greater than or equal to 0, or minus x. We don't like piecewise functions. It's more convenient to just square it. Now that everything is positive, you can take the average or the mean. Those are, same thing. But again, once we square it, we're dealing with velocities. We're not dealing with velocities anymore. We're dealing with velocities squared. So in order to get back to the right type of thing, to get the right units, then we take the square root. And so this velocity that we get by going through this process, the average we get, we call that VRMS, where this stands for root mean square. So that's we square everything, take the average or mean, and then the square root, so R. So if you see that RMS, which you'll see a few times in this class, yeah, that's basically what it means. You square it to make it positive, then you take the average, and then you take the square root. And because this distribution is skewed to the right, the RMS average is going to be a little bit beyond that peak value, because there's no real limit to how fast they can be moving. Well, obviously, there's practical limits, but there's definite limit of 0 for they can't be moving less than 0. And so yeah, it's not a symmetric graph. So the peak value and the RMS average are a little offset. Now another thing Maxwell was able to do, which is very, very impressive, he was able to show that the average kinetic energy of a molecule in a gas, an atom or a molecule, was 3/2 kT. So this is the average kinetic energy of a molecule. And so really it only depends on the temperature. And that by itself is a pretty amazing fact, because it doesn't matter what molecule you're talking about. You could be talking about helium or radon. Helium is, of course, a very light gas. Radon is a much heavier gas. The molecules are much bigger, or the atoms in radon are much bigger. But if you look at the average kinetic energy of any molecule, at a given temperature, it's always going to be the same. Now, this kind of breaks down when you go near absolute 0, but otherwise, it's a remarkable result. And the way it works is that like the lighter molecules move faster. So they have the same amount of kinetic energy as the heavier ones. And again, Maxwell did both of these. He came up with this velocity distribution, which I probably shouldn't have erased. Yeah, he did this in the kind of mid-1800s. I guess the second half of the 19th century he did this. And it took a long time for them to actually confirm this experimentally. And there's a really interesting apparatus that they came up with to do this, to actually measure the velocity of a gas. And what they did is they had an oven where they could melt things and form a gas. And so you've got molecules coming out. And let's say we put this series of plates here and put holes in them. So basically, if something comes out of the oven, it'll hit the wall here. This wall's going to block them unless they're coming directly out. So we can create a beam of particles if you have like a couple walls to keep things. So you have this kind of a narrow beam of molecules moving in one direction. And again, you can control the temperature of this gas by temperature of the oven. And so they designed this really interesting experiment where you have this cylinder. I'll just draw a cross section. Where on the edge of the cylinder you have this thing cut out that looks something like this. And this beam would enter here. And obviously, if just looking at the picture, the beam enters, what's it going to do? It's going to hit this wall, and nothing is going to happen. Nothing's going to come out the other end. However, what they would do is they'd rotate this cylinder so that as the particles are moving, this is rotating upwards. And so, like once this gets over the wall, well, this whole thing is moved up a little bit. And if you rotate it at just the right speed, for a given velocity, these particles are going to pass through. Like the wall's going to move away at just the right rate so that it's going to, pass directly through. So that's one way you could experimentally measure the velocity of these particles. See, and knowing the angular velocity that you're rotating the cylinder, you can tell the velocity of the particles that are getting through. And of course, they were expecting a distribution of velocity. So you start out rotating this slowly, and then these slow particles are going to make it through. If they're going too fast, they're going to hit the wall. If they're moving too slow, the wall's going to come up and hit them. This lower wall's going to hit them. So it's only if they're going at just the right speed that they're going to make it through. And so you start out, there's a relation between the angular velocity and the velocity of the particles that make it through. And so what you can do, because there's a whole distribution, you can rotate at a particular velocity and just see how many are getting through. And I suppose one way you could do that would just be to collect the particles and either weigh them or collect them in a container and find the pressure, which would be proportional to the number of particles. So you can spin it through at one velocity and somehow measure the amount that get through. And then you do it for a different velocity and you get a different amount, and then you could recreate this graph, and it works extremely well. So Maxwell calculated this curve, and it was experimentally verified. I think it took till the 1950s to really do this accurately and come up with this experiment and get a very accurate reading. But yeah, so that's one thing Maxwell did. The other is this really remarkable thing that the average kinetic energy of this would be any given atom or molecule in a gas, is 3/2 kT. Now, I want to talk about the gas overall. So we talked about internal energy a while ago. So say we have a gas in a container, and we look at these molecules in the gas, and they're moving around. They automatically have kinetic energy. Now, so remember the average kinetic energy of a single molecule is 3/2 kT. And so the total kinetic energy is going to be 3/2 nkt. So basically the total kinetic energy would just be the number of particles times the average kinetic energy of an individual particle. So this would be the kinetic energy of a gas. Just the overall gas. But it's possible for a gas to have other forms of energy. Every gas is going to have kinetic energy. But it's also possible to have rotational kinetic energy. Like say you have say nitrogen. Or just in general, you have a diatomic molecule. It's possible it could be rotating. So I picture this molecule. It could literally just be there's an atom on each end. And it could rotate, and it'll have rotational kinetic energy if that's the case. Now you might think, why? Now I said it can rotate. For reasons that we can't really get into here, it has to do with quantum mechanics, which you may have heard of that word before. But it depends on the temperature. It's like at low temperatures, it's not going to rotate. At room temperature, it might. It depends on the gas, but only for diatomic gases. So the types of internal energy it can have, it depends on the gas. So all gases have kinetic energy. There's also rotational. And this would occur for diatomic gases, but only if it's high enough temperature. At low temperatures, they don't have enough energy to rotate. So one of these things when, you might have heard the term quantum mechanics without necessarily knowing what it is. But the idea in quantum mechanics is that everything is quantized. So just like the number of molecules is quantized. You can have one molecule or two molecule, three, but not like 1.5. Turns out energy is also quantized. And so if a gas is too cold, they just don't have enough energy to rotate. And then again, for diatomic gases, you can picture them, there's forces of interaction between them. You can kind of picture that like a spring. And at high enough temperatures, they can oscillate as well, which gives them more kinetic energy. And so there's three forms of energy that are possible. And again, this would only occur for like a diatomic gas, not a monatomic. And of course, molecules get more complicated, like H2O. So again, we're not going to get into all these details. But the basic picture, if we look at the internal energy as a function of temperature, it's going to depend on what types of energy it has. So it depends on whether or not we have, if we have a monatomic gas, like helium or neon, there's more, like that whole column in the periodic table of noble gases. Those are monatomic. The internal energy is always going to be 3/2 kT. 3/2 nkt. It's just that kinetic energy. But for a diatomic gas, it's going to look like this. The internal energy, not exactly to scale. This bottom should be a little bit lower. But, yeah. And again, it depends. There's like certain temperatures where like once it's in this range, so like this is just translation. Now this say T. This is translation and rotation. This is translation, rotation, and vibration. And so obviously, more energy, the more things it's doing. And we're not going to worry too much about the details here, because typically at room temperature, we have translation and rotations. So the end result is the internal energy of a gas under normal conditions. And that's what we're going to use. The internal energy of a gas is 3/2 nkt for a monatomic gas. Or 5/2 nkt for a diatomic gas. And again, it's important to understand that this only occurs in a certain temperature range. If you have a diatomic gas at a very low temperature, the internal energy would be 3/2 nkt, just like a monatomic gas. But at room temperature, it would be 5/2. And if you go to very high temperature, it would actually jump to 7/2. So it kind of jumps. But we're just going to stick to normal temperatures. So this is what we're going to use in this class. Monatomic gas, 3/2 nkt. For a diatomic gas, 5/2 nkt. Okay. So that's going to be it for this distribution of velocities. So again, just if you look at any gas, that picture, kind of that picture in your mind, that tells you like what fraction are moving at a particular velocity. I didn't give you numbers. I have something for oxygen. It's in the notes. Let's see, for oxygen at, say, 300 Kelvin. So that's around room temperature. So the RMS average is 484 meters per second. So that'd be for O2. And then if you go to 1200 Kelvin, it would go up to 967 meters per second. So again, this isn't extremely fast, and that's an RMS average. So some are going to be going slower, some will be going faster. But again, that's moving very quickly. And oxygen's not a small molecule. If you look at hydrogen, a hydrogen molecule has 1/16 the mass. 1/16 the mass, so it's going to have to be moving a lot faster because every molecule of hydrogen is going to have same energy on average as a molecule of oxygen. So it'll have to be going a lot faster. But yeah, the main things, just have an idea of that velocity distribution chart and also internal energy. So we have this average kinetic energy of a molecule depends just on the temperature. It'll be 3/2 kT. And again, absolute temperature measured in kelvins. And then also this idea of internal energy, where we're going to keep it simple. It's either monatomic or diatomic gas. And we're always going to stick to like that room temperature range where we have either 3/2 or 5/2 nKT for the total internal energy of a gas. So yeah, really amazing that it doesn't even depend on what type of gas, just on the temperature. All right, so that'll be it for velocity distribution. Okay.